Hello everyone, my name is Ashfaq Ahmed and I'm working in the field of bioinformatics and structural biology. Today I will show how can you perform docking in automated setup. We call it Google Colab. To perform docking by this method, you will be hassle-free from installing any software into your operating system. The title of this video is Molecular Docking on Google Colab. Here is a disclaimer and you need to read it and understand it. What actually molecular docking is? Here is a brief introduction of molecular docking. Identification of the ligand's correct binding geometry in the binding site or in the active site. So, it means from docking we expect the correct binding pose or the correct geometry in interaction. It also means we do not need a simple patch-up of compounds and proteins. What is automated way of docking? In this way of docking, or in today's video, we will particularly learn how to use a receptor directly from PDB, or I would say how to use a protein directly from PDB. PDB is a database that contains the structural information of proteins, or simply I would say the structures of protein. If your receptor is not present in PDB, also don't worry, I will come up to that in future video or in other videos that how we will deal those stuff. So for now, this video is more important for those whose receptor is present in the PDB. What are the merits and demerits of this method of docking? Merits, it is faster. Of course, you will see it's faster. Second, you can dock single or many compounds. Doesn't matter you have 1000 compound or 10 compounds or one compound. Another merit I discussed earlier, by this method you will not be required to install anything into your computer and you will be able to perform docking. Another merit which is not present on this slide, after docking, or I would say post docking analysis, it will be very easy for you through Google Colab. Therefore, I choose first to teach you docking by Google Colab, then after that I will teach you by other methods, so it will be easy dealing the other methods. But what are the demerits of this way of docking? Number one, it needs internet. So you must have an active internet connection. If you don't have, you cannot perform docking by this way. And sometime you may face this issue because Google Colab using the libraries from the cloud. So sometime a company or those people who has written those libraries provide an updated version. In that case, some of your library or some of your program may give you some error, but don't worry, these problems are coming on daily basis and people are solving them also on daily basis. So let's start how we will perform such kind of docking. So what you need, let me minimize this window. Also, if you like my videos and if you want me to continue, please support in the form of subscription. You can see my channel, I don't have much more subscription, but in the form of a subscription, I feel encouraged and I provide time and I make such kind of videos. Okay, let's start. So first you need to open Google Colab and the repository I made it for you. How will you open? Just type colab.research.google.com/github/ash100. I will also drop this link in the description section of this video so you can directly copy and paste it into your browser. Enter. Okay, when you see this kind of window on your computer, you need to click here and select DAS ASH100 DAS. You will see two kinds of files. You need to select the first one, DAVS. That stand for, actually it is not stand for, but I made a name like this, docking and virtual screening. Click here. Okay, now you need to connect here. So it may take a while, just probably 10 seconds, and it will be connected. You can see this icon, RAM and disk. Now here is a brief introduction about this channel. This is channel link. Okay, we will use these softwares or these programs. It includes MGL tools, Open Bible, Py 3D Mol, etc., Vina and Conda Colab, and you will need to cite all these programs when you finish your study, okay, and during your manuscript preparation. Okay, now the next step is the first topic you can see, or the link you can see, installation of the required packages and dependencies. So currently you don't need to change anything here. Just click this play button and it may take click here run anyway. It may take 2 minutes or 3 minutes, depend upon your internet connection. So I'm going to pause this video for a while. Okay, once this process is finished, you will see this kind of notification about unknown crash. Cancel it, because upon successful completion of this first step, this notebook will restart itself. So that's why. Now the second step, we will import all the programs to our this session or this notebook. So if you don't want to see the code, just click here. Okay, run this, and it may take almost 5 seconds. Okay, you can read it. Import it, done. Environment is ready for molecular docking. Now see here, you can see this folder option. If you click it, you will see two things. One is the installation log. It means what you have installed in previous step, and this one is the Vina folder which we installed previously. Now we will create a directory here, and your directory should contain your name which you selected. So create a folder, you can see, or create a directory. So here I will use the name, let's say 4EXS. Why I'm using this name? Because I will use this protein for docking. So therefore, otherwise it is up to you which name to use or not. Okay, so just type the name you want to use here and click this link. Okay, and it says folder created, and this folder 4EXS folder created. This folder contains subfolder proteins, ligand, experimental, docking folder, and interaction folder. You can see here 4EXS. If you click here, you can see 1 2 3 4 5 subfolders. Okay, now the next step, we will set up some utilities. So you don't need to change anything, just click here. Okay, done. When a code is successfully run, you will see this tick mark. Okay, now we will prepare our receptor molecule from the PDB. Okay, so you need to open the PDB rcsb.org. Okay, that's it. I don't know what it say. Probably I made some mistake, therefore. Okay, rcsb.org. Now you will see a search bar here. So you will need to type your protein. For example, I know my protein is 4EXS, so I'm going to open that protein here. Here it is, 4EX. You can see it on the PDB. Okay, here is an important question I want to address. Sometime you may have many proteins for your receptor. For example, you are dealing, this is called NDM1. For example, you are dealing NDM1, and if you type NDM1 in PDB, then you will see many structures, maybe 10, maybe 20, maybe 30, or so on. If you have this case, if your receptor has many structures in PDB, then which one you will select? This is an important question, so I want also to address it here. What type of receptor is preferred to select from the PDB? If you are using this method, the Google Colab method, then you have to take care for two variables during receptor selection. One is the resolution, another one is to select a structure having a ligand molecule already. The resolution you can see here, 2.40. For example, I give you an example like NDM-1. Let's say I don't know how many structure it has. I'm searching and I will see this kind of window. You see, all these are NDM1. Okay, so which one I will select? The one having low resolution. Low resolution means you can see X-ray diffraction 2.0, X-ray diffraction 1.8. So if you ask me which one is better among these two, this one is better. The resolution is lower. In digital term it is lower, but in scientific term we call it higher resolution. So don't confuse yourself. The higher resolution will always have a lowest or a lower value. Okay, now this one is 1.4, which is better than both of them. Okay, so this is point 1. Always select a structure having low resolution, and this is point 2. Select a structure having a ligand molecule already. So if you have, let's say 1, 2, 3, these 3 structure, then which one you will select? Just read the title. Crystal structure of NDM1 at pH 5.5 in complex with hydrolyzed penicillin 5. It means this structure already has a hydrolyzed penicillin. This one contain hydrolyzed compound 1. You can also see in the picture it has a ligand molecule, so it's better. And this one also has probably it has some molecule here. It says affinity level, maybe it has, but if you don't know whether it has or not, if you are not clearing from this title, then simply download the structure. I taught you in previous video. Just click here and then you will see, for example, here I'm going to 4EXS. I'm going to the same structure. So when you click it, you will see this kind of window. Then from here, download files and click the PDB format. Once you download your structure, open it in any visualization, whether Discovery Studio, PyMol, ResMol, Chimera, MGL, whatever. So open it and you will see there that whether it contains a ligand molecule or not. Another question may comes in your mind, that if we select a structure having a ligand molecule, why we are not selecting a structure without a ligand molecule? So the answer is that this program, we are dealing this procedure in this one. So in next step, we will choose our grid box. We will choose our area for molecular docking. We will choose the area for the active site. So therefore, if the structure already contains some other ligand, then we will ask the program to use their specific area. It will be very easy for us. But if there is no structure with a ligand, in that case you will ask the program which area to select. So this is the difference between a structure with a ligand and a structure without a ligand. Also, you may have a question why to select a higher resolution. I mean a resolution with lower value, because the higher the resolution, the better the structure, and there may have very little missing residues or some other problems in the structure. And lastly, try to select the structure solved by X-ray crystallography or X-ray diffraction or electron microscopy. Try to avoid the structure solved by the NMR method. It's a different debate. We will talk in some other time. Okay, so for now I suppose you will be okay with the receptor selection and how to select your receptor. So in this case, our receptor will be 4EXS, which is solved by 2.40. Don't worry, I select this receptor just for a tutorial purpose. If I'm going to make a genuine research, then I will not select this receptor. I may select the one with the lowest higher resolution or the lowest value of resolution. And this structure has a ligand molecule. If you come here, it has a ligand molecule X8Z. This is the ligand ID, and its name is captopril. Captopril is actually a cardiovascular drug, and this is the 2D diagram of the captopril, and this structure also contains the zinc atom. Let me clear another point for you guys here. Sometime, or I would say most of the time, people are messaging me and they ask me that our structure contains magnesium ion or zinc ions or calcium ions, etc., etc. So can we say it a ligand? Of course, anything without a protein structure is technically a ligand, but here in docking, from the ligand we refer a molecule, a drug molecule, some organic molecule. So in docking scenario, the metal ions, I would say, do not consider them as a ligand. For further details, you are advised to watch other two videos like the protein research, and I have explained there that why these metal ions are present in protein and what is the importance of these metal ions. Okay, so also sometime you will see in this ligand category some salt molecule, just like I would say sulfate, SO4, and sometime GOL or glycerol molecule. So do not consider them as a ligand also, because these molecules come with the structure from the experimental setup. You will say, what is the experimental setup? Someone has solved these structures. Of course, in some country, in some lab, someone has solved these structures. They have used different salts to crystallize the protein. So these are actually the experimental debris, I would say, the experimental waste which left with the protein, and how you will understand whether they are experimental or not. So there are two ways to understand. First, open the structure in any visualizer, then you will see that these particles are not inside the structure. They are some in scattered position or in the surface. So that is one indication. Another indication that if you read their paper of that protein structure, you will not see any discussion or in any importance of those things in the result. So you will understand that okay, they come from this specific salt they have mentioned in the methodology section. So to conclude this section, for ligand, do not consider the ions as a ligand. Do not consider those waste, I would call it waste materials, just like salts, particles of salts like sulfate, CO3 or other things, or glycerols, etc. Or because they came from the experimental setup during crystallization, in normal scenario they will not be present. Okay, and so what left with us? An organic molecule or a drug like captopril. Okay, so now let's come back here. We have created a folder up here. Now preparing our receptor molecule, so we will write the PDB ID of our receptor. In this case, the PDB ID I will use is 4EXS. If in case your PDB ID is different, change it here. It's editable. Change it. So I will write again 4EXS and click it. Okay. PDB downloaded 4EXS into protein folder. You don't worry, it's here, protein folder. Here it is 4EXS.pdb. That's it. Now next step is to extract protein. Sometime the proteins are coming with symmetric structures. Symmetric I mean in dimer, trimer for easy understanding, or simply I would say you will expect one chain, but once you download it from the PDB, you will see 2, 3 or 4 different chains of the same protein or mirror images. In that case, we will extract or we will generate a clean protein structure for molecular docking, and the protein chains will be extracted into separate files. So click here and read this section. Protein extracted 4EXPDB, chains detected. So it has 2 chains, B and A. So the program name it or extracted 4EX underscore prot underscore B, 4EX underscore prot underscore A dot PDB. Both are present in the protein folder, prot A, prot B. Okay. Now it is up to you which chain to use for molecular docking. Here I will use the prot A. If your protein do not have any structure or chains and only one, so change that name here. In my case, I will use, let's say, the chain B. No, okay, I will use chain A. Okay, if you want to see your protein or the chain of your protein, so you can use this panel, view chain A. Which representation I like? Cartoon, so cartoon. I like white color. I want to focus these residues. It's not necessary, it's just a visualization. So even if you don't want this visualization, just skip it. But for a proper explanation, I will run it for you. It may take 10 to 20 seconds and that's it. I think 9 seconds. Okay, you can see here showing 4EXProt.a. so now you can, it's zoom. I am going to zooming out. Now see a very beautiful picture of my receptor. Why these residues are like this? Because I have focused these residue. If you don't want to focus anything, just set it blank. It will be run again and you will see this thing without those residues. See here, nothing has been focused. Okay, the next step is parameterization a protein with Gastier charges. Normally we are doing this step with MGL tools, but here we will do it in automated way. It includes the generation of PDB-QT files and some docking files. So you can also read it here. The generation this generate a protein.pdb file. It adds partial charges, it adds hydrogens or polar hydrogen, and it removes the non-polar hydrogens. So we are dealing with this protein or this chain, so click play. It's done. It says we have generated .pdbqt and it is present in the docking folder. You can check it here. It's here. Okay, so far so good. This thing, extraction of the experimental ligand, I have explained it in a sufficient detail earlier on, that select a protein or select a receptor which already has a ligand molecule. In this case we have X8Z, but in your case it will be different. For example, how I will know? This is 4EX my protein. Come here. Here this is the section for ligands. It says 2 unique, but this one is the zinc ion. I talked already, and this one is our ligand molecule. So in your case, maybe this thing is different. Maybe here is E23 or XYZ or whatever the name is. Just write it here. In my case, here we have X8Z. Once you write it, click here. The program will detect the ligand and will extract it, will remove it from the structure, and will save it separately with the name x8z.pdb. You may see it here, not here, maybe in the docking section, no, maybe in the protein section. Okay, it's present here in the experimental section because this ligand came from the experiment. So that's why x8z.pdb. Extract experimental ligand. Here this step just told you like which one we extracted. So just to confirm the cleanness of the experimental ligand, we will run this again. In case if you experience some error, just read here. It will say that most of the time it will say we cannot find this. So just double check from here whether I have wrote this name same or made some mistakes. Okay, so they have extracted x8zb.pdb, x8z_a.pdb in experimental folder. You can see here. Why 2 ligands? If you remember earlier on, this protein has 2 chains, and every chain contains its own ligand. So the chain A contains this ligand, the chain B contains this ligand. So simple. Now I want to display the structure of the X8ZA ligand, or if you want to see the structure of another ligand, so that's okay. Don't click it here. First change the name here. Which one among these 2 you want to see? I will use the chain A, therefore I want to see this ligand, the A. So click here. You can see here, this is our ligand molecule which came from the experiment, and its name is L-captopril, which is a cardiovascular drug. If you want, after seeing, you can cancel it also, doesn't matter. Okay, the next important step is ligand preparation for docking. This is a very important step and you need to understand it. What we will do, we have downloaded our protein. Okay, we have okay, welcome back. So we have downloaded our structure. Here we made a clean copy. Here we removed or we extracted our ligand here. That's it. Now we will come to the selection of our own ligand or own compounds which we want to dock. You can take these ligands from anywhere, but in this tutorial I will take them from PubChem. So how to prepare the ligand list, just watch. Okay, I'm going to open PubChem. Oh sorry, okay. Okay, currently I don't have any ligand, so I will select just randomly 3 ligands. Okay, so let's say I'm selecting one Panadol. Actually Panadol is not a Panadol is a brand name. I will say paracetamol. This is a compound name. The paracetamol, or it's also called acetaminophen. So here it is. Okay, how this program or how our program will keep this data. So let me teach you. I will use this folder. Okay, you will need to make an Excel file, Microsoft Excel worksheet. I will name it just like ligand. Okay, I will name it COMP compound _1. That's okay, and open this file. Okay, we will use the A column and the B column. In A column you need to write in capital. Again you need to write in capital ID. In B column you need to write smileys in capital. What is ID? What is smileys? So this is the compound. This is actually the ID, compound ID 1983. But it is up to you which name you want to use in docking. So you can, here I will not use 1983 just to make things interesting. I will use this name, paracetamol, but you can use whatever 163, whatever you want to use. Okay, the next what we will put in the smileys, you can see here isomeric smileys. Just copy. Okay, Control C and paste it here. Okay, now let's say my second compound is ibuprofen or ibuprofen, whatever, ibuprofen. Okay, let's take this one, copy smileys, Control V, and I will name it ibuprofen. Okay, let me select a third one also, and I will select what to select. Okay, let's say I'm selecting anything. Cefixime, it's an antibiotic. Oh, maybe okay, I select azithromycin. Okay, that's it. That's fine. It will take a bit longer maybe in docking because it's a longer structure, but let's see. okay, azithromycin. So just Control V because the structure is bigger, okay, and I will name it azithro. Okay, so you need to mention your list of compounds here in the same way, 3, 4, 10, 100, whatever they are. Okay, here I want to give you another interesting idea. Last time, I will drop a link here. Maybe you have already a list of compounds, let's say 20, 50, 30. So I would suggest to check them in this stage or after the docking stage, whether they are toxic or not or mutagenic. So for that you can see my shorter video here on the channel. Its name is, okay, it's not open. Okay, you can search it by yourself. I will also drop a link there. But also, for example, this is the second point is for those who has only one compound or who has only two compounds, and if they want to make their study bigger. So how will you make your study bigger? How you can dock many compounds to your receptor? The answer is very easy. I have a video another on this channel. The video name is how to mine PubChem database for similar compounds. So you just provide your own compound and collect, let's say, 100 more compounds based on the similarity, 80%, 90%, that is up to you. I have explained each and everything in that video. So you will have a list of 100 compounds similar to your one compound. Now you can check which one is better. Either your compound is better or those similar to your compound is better. So I just wanted to tell you that you can make your study more fruitful rather than to dock one compound. But it's okay. Let's move on. After making your list, you need to click File, Save As, and here in Save As, I'm saving this file, compound 1, into CSV Macintosh. Remember, CSV Macintosh. In this section, Save As type, CSV Macintosh, name is compound underscore 1, click Save. It will give you this option, click Yes, and minimize it for right now. Okay, now we have our list of 3 compounds. What we will need, we will click here. You see the 4EX folder we have. This is the ligand folder which is empty. So you will click on these 3 dots and upload your file, the CSV file. These 3 dots, click, you can see upload. Computer will ask you from where I need to upload. You say desktop, 1, 2, 3, upload compound 1. So we have 2 files of compound 1. This will be the Excel file. You can see type Microsoft Excel, and this is the CSV file. So we will upload this CSV file, CSV Macintosh. The computer will ask you that you are uploading some file. You say okay, and according to your file it will take some time. In our case it was a smaller file, so it is uploaded here. Now what is the file name? Compound underscore 1.csv. So you need to edit here like compound underscore 1.csv and click this button. That's perfect. We can see three files, three compound, paracetamol, ibuprofen and azethro, and these are the smileys and these are the IDs we created. If you see this thing, it means your compounds are uploaded. Now we will convert these smileys interpretation into a structure. So click here and they say that 3 ligands are generated in the smileys folder. One is ibuprofen SMI, azethro SMI and paracetamol SMI. Now we will want to see the structure if you want to see. So here I wrote pmol, you just don't write pmol. Let's say I want to see ibuprofen structure, ibuprofen, and if you want to see some label, click here, otherwise don't click here, click play. This is ibuprofen. Okay, if you want to see let's say azethro, this is azethro structure. It's a bigger structure, I told you already. This is azithromycin. Okay, so I'm not going to check the third one. It's okay, it's working. Third step, parameterize ligands with Gastier charges. Now we will prepare all these 3 ligands, and we subsequently what we will do these 3 steps. First, we will generate ligand.mol2 and also we will generate ligand.pdbqt, just like we created for our receptor. The second thing we will do, energy minimization. By default I have set 10,000 iteration time for minimization, but you can increase this step further. I will not suggest to decrease it because sometime in your library you may have different structure or very strange kind of structure and it needs much more iterations. So therefore by default it is okay, although you can increase it, but you need to remember it because during your thesis writing or manuscript writing you will need to include these information in methodology. We will also add Gastier charges, we will remove some non-polar hydrogen, and lastly which force field we want to select for these operations. So we have options of GAF, chemical, FF94, FF94S and UFF. Normally people are using GAF and UFF, but sometimes some of the compounds are not parameterizing successfully with some of them of these force field, then you will need to change your force field. Okay, also remember, sometime when you generate your compound library or compound list, so most of the time you will see a dot here and then some other name like calcium or sodium, etc. If you see something like this in your structure, you are allowed to remove those salts residues from the smileys, otherwise you will experience some problems. Okay, currently I'm using the UFF and I'm using the 10,000 iterations, but if you want to increase it, so here is the place: force field steps 10,000. Just change this green 10,000 to 15,000, 20,000, whatever you want. Click here and wait for some time. From here it says 2 of 3, it means 67% completed. 2 compounds are treated, the third one is still remaining. Okay, it is important to read here this information, to read it. Why? Sometime you will have, let's say, your list of 100 compounds, and here it will say we have prepared 98, and if you do not read this step, these results or these notifications, then you will face error in next step. So here we had 3 ligands, all of 3 are prepared and in the docking folder. Let me check. In the docking folder we have 3 more folders. Paracetamol, it contains paracetamol.pdbqt, azethro will contain azethro.pdbqt, and so on. Now here we reach, we have just give me, I'm going to pause this video. Okay, welcome back. We have prepared our receptor molecule, we have also prepared our ligand molecules. Now we are moving to some operational section. Setting of molecular docking, you need to read this, otherwise if you don't want, that's okay. We will select grid box now. Grid box is technically the place you want to dock your molecule where. If you want to dock your molecule to a particular place, so you need to mention for the program like dock it here. So that position is called, or that place is called the grid box. We will set the coordinates. But in this case, if your receptor, if your proteins contain a ligand molecule, like in this case we have L-captopril from the experimental ligand from the PDB, so it's very easy for us. We will ask the program use the location taken by L-captopril. So that's why I had asked you in the start to use a receptor molecule with a ligand. Okay, so here you have 4 or 5 options: LabBox, eBox size, manual, autodock grid. If you know your grid file, that's okay, just manually set it here. X will be like this, width will be, you can move these things. But again, if your structure contains a ligand molecule, then choose the LabBox method. If you know residues from the literature, just type those number here and the grid box will be selected automatically. In this case, I'm using LabBox method. It's an automatic method, and just click it. Wait, okay, some mistake probably. So we were receiving some error because I forgot to click this tip, that was choose experimental ligand. So I came back, I run it again, this step. It will not be a problem for you, don't worry, until and unless you click all the steps. So I just click lawbox method here and run this cell. Okay, now you can see here, this is our receptor molecule with L-captopril, and that enclosed our own grid box. It means this is our grid box, and these three ligands will come here or will take this space. Let me pause this video again, my backup is running low. Okay, so here we are. We have also selected our grid box. Now if you want to cancel it, you can, because this step has been successfully completed. The next step is we will generate a configuration file using the above grid box. So we don't need some extra step, just click here and it will automatically generate a configuration file in the docking folder. You can review it here, it's here. You can also use this configuration file if you want to use it in offline setting. We will cover docking in offline setup some other time. Now technically we will perform, or we will run the docking stuffs, the docking programs. One thing you can change, if you want, the exhaustiveness value by default it is 8, but if you are dealing with some unknown compounds or more than one compounds, so I would suggest you increase it at least up to 16. The exhaustiveness value actually deals with the compound rotations. If the compound has many rotatable bonds, it means the program needs much more time to calculate the correct binding pose. It means the compound will make more conformation, more variations. Therefore we will allow the program that you take much more extra time, much more extra cycles, iterations I would say, to fix our compound in a correct pose. So that's why I would suggest to use 16 at least if you have some unknown compounds or many compounds. Of course it will take a bit higher time, more time. Here in this case I will use 8. That's okay because we are running a tutorial. So just click here, run autodoc. So you will see this window here. It will start from 0 to paracetamol took 8 seconds, 8.2 seconds, and done. I will pause this video for a while. So you can see now our docking is finished. Paracetamol take 8.2 seconds, ibuprofen take 22 seconds, and azithro take a longer time, almost above than 1000 seconds, and in total it took 23 minutes. You will be surprised that why this longer time, because azithro contains a very complex structure. So therefore for such compounds, the program normally took longer time. But you do not worry, such compounds are very limited. Most often your compounds will be dealt very quickly and effectively in this notebook. Okay, so now the beauty of this notebook is to process your file quickly and effectively. So the first process, we will process the output which are generated here. So if you see here in docking folder, we have paracetamol, and this is the output file which is generated. This is the log file generated in the pdbqt file. Okay, we will process this file now. So we will click here. It says I have processed 3 ligands output in the pdb in the docking folder, and 19, it has generated 19 files. Let's say what it has generated now. That's what I wanted to see. Okay, this is the paracetamol pdbqt file. This is paracetamol 1 2 3 and up to 9. These are the different poses generated by the docking program for every ligand. Now we will calculate the binding interactions offered by these ligands in one go. We will use a plip program about plip. I have already made a video, so you will be aware of it. Okay, just click here. It has generated some file in interaction folder for paracetamol. For all the 9 poses, it has generated interaction. Likewise for azithro, we have 1 pose possibly, so that's why. And for the ibuprofen, for all the 9, it has generated interaction. Okay, now protein profile protein ligand interaction, we will click this and it will generate a CSV file in every folder. Interaction folder, we can see a CSV file. I'm not seeing where it has generated 19.csv files. Wait, you can also refresh it maybe. Yeah, here, this is for this is for this. For every pose we have a CSV file. Now the next step is to visualize the docking result. If you want, you can visualize. So generate docking results, click here. All the results are generated and we will rank our result now. We will rank 3 things: the RMSD in LB and BP mode. LB means lower bound and BP means best pose. Lower bound and upper bound and best pose, and RMSD versus experimental ligand. So once we visualize it, you will understand it. Okay, done. Okay, so the best rank compound, you can see that it's azithro. It took it generated minus 12.792 a score with the RMSD of 4.620. On the second tier we have ibuprofen the first pose, and it generated minus 5.3. On the third tire we have paracetamol with this RMSD and this score. So you see, I deal only 3 compounds. In your case maybe you have 100 or 200 or whatever, so you will have all this result in one go. Now I want to see docking result of some molecule. So let's say I want to see the result of Azithro underscore 1. So you just type here Azithro underscore 1 and click here. Maybe some error. Why? No, it says no such files or directory. Wait, let me try. Why it says Azithro in the docking folder? Okay, then Azithro. Okay, Azithro underscore 1. Azithro. Did I made any mistake? Azithro underscore 1. Okay, let me try some other, then we will see. Ibuprofen underscore 1. Ibuprofen underscore 1. Okay, so this is, oh, I got it. We will enter. Okay, you will need to enter the name of a ligand. So ibuprofen. So these are all the 9 poses of the ibuprofen. Among them, the first pose, which generated 5.3 with RMSD this and with other RMSDs this score, and it's the same thing. The top one is here. So we will choose, or you will choose the first one from ibuprofen. Now for paracetamol. Okay, this is for paracetamol, all the poses. Now I will type Azithro. Okay, actually we have one pose for Azithro, so that's why, and I will tell you why this is one. Okay, show interaction profile of ligand. So which ligand? Let's say I am interested in the first one, ibuprofen, but underscore 1, because it is our best compound from the ibuprofen. So you can see the ibuprofen 1 make these interaction. It makes 4 salt bridges with this distance, with which residue? Histidine 120, 122, 89 and histidine 250, and it makes 3 hydrophobic or van der Waals interactions with valine, tryptophan and again tryptophan. With these are the residue number. RS and R means residue number. The same you can, why Azithro scored -12. So we will find out. Azithro underscore 1. Wow, because it has 5 extra hydrogen bonds with these residues, 3 hydrophobic van der Waals hydrophobic interaction and 2 salt bridges. So of course the number of interactions are clearly different for Azithro. So you can also make this kind of data for your ligands. Now if you want to display, for example, I want to display this one Ezithro underscore 1, then what you will do, you will view protein this one, which model, like I want to use cartoon model, white color is best, focus residue, leave it, residue color white, or if you want to change it you can. Show all subunits, okay, don't check it. Show residue label, okay. Show interaction, yes. Show van der Waal surface, yes, okay. Then the ligand mode, which ligand you want to see, I want to see Ezithro underscore 1. And do you want to see the experimental ligand, then here is put the name. In my case it was X8Z, so yes, show ligand. Now after selecting all these things, we will click this option and you will see the magic. Okay, what is the magic? Here is the magic. Okay, the yellow color compound is actually Ezithro, and the black color is the experimental ligand. So this is one confirmation that Ezithro took the same space which was taken by L-captopril. Okay, if you don't want to see the native ligand, just click here, show experimental ligand, turn it off, see again. Now you will not see anything. Okay, this is our azithromycin and interaction with those residues. The interactions are already explained here, that what kind of interaction they are making. Okay, by this way you can visualize each and everything. Finally, of course I will not suggest you to take a screenshot of these figures, because it will be a lower resolution and it will not work. So for that you will need to generate to save your data into your Google Drive. Every one of you have a Google, I know, because it's sign in here. So just click here, click the import Google Drive option. Once you click it, you will have this kind of option, connect to Google Drive. You say yes, then you will have, I will use my ID right now. I click here, it will give you this option. Now continue, because it's taking access to your Google Drive. Again continue, and you will have an option like the drive is mounted. It is just like you plug a USB of your Google Drive. Yes, here it is. Now I want to save my data, and I will name it like test underscore NDM1, sorry, NDM1. Okay, and click here. Congratulations, we are done. But just hold on 2 minutes more. I'm going to open my Google Drive, G Drive. Click here, go to Drive, okay, we click home button or my drive, whatever. Let's say I'm clicking home button, my drive. I should have that folder here, test NDM1. Okay, let me click here and download. The magic is here. It will take some time because files are zipping. Okay, files were zipped. I had paused and now I have downloaded. So I will check it my download folder. Test NDM1. Okay, I will cut it from here and paste it here in a separate folder, just not to mix it. Let's say I will say NDM1 underscore test and paste it. Extract here. Test NDM1 was the folder name. 4ex. It has these 4 folders. Now what you want, if you want the docking result, so these are your docking results. These are the Exhaustiveness underscore 1. This is the output. In case of ibuprofen, we have all these outputs already. PDBs are generated. This is the output file generated by the Vina, you can see. So you will not need it more, but and this is the complete result of ibuprofen. We already visualize it in our portal. This is the post score. So if you want to use it, although the program told us what were the best or top compounds, in our case top was Exhaustiveness 1, ibuprofen second, and this third. Now the last thing is you will need to generate some beautiful figures. So for that I have already generated a video for you. So these 2 videos, download your results and learn these 2 videos, how to generate protein ligand images and generate your images for tables. There are Excel files you can generate from there, and how to make your compound library bigger. If you have one compound, just follow this video, how to mine PubChem database and make your library bigger for docking. And finally, how to check the toxicity of your compound, of your library. For this we have this video, and for publication we have this video. So right now I have completed the automated way of docking, and from next time I will teach you the other ways of docking if you do not have internet or some other problems. That's it for today. I know it was a very longer video, but I was not just to complete things quickly in a hurry. So I tried my level best to provide each and every explanation. Still, if you have any question, you can ask me in the comment section. Also, I'm planning to start coming YouTube with a YouTube live online, but for that I'm waiting for the feedback. So let's see. I hope you will enjoy this video, and if I don't look good, but still I have to say, if you are enjoying my videos, if you want me to continue this journey with you, so support me and encourage me, and for that support I need your subscription, so that I can feel that I have some people are listening me. So that's actually the encouragement. Thank you very much, and drop your feedback in comment section. Bye bye.